sorry guys, we had to cut the video short on the first one just because I had a class that was coming in. We ended off with talking about bond order. So the bond order is 1/2 the difference between the number of bonding and the number of anti-bonding. Ultimately bond order, so like this is how you would find bond order, which we'll do in just a second. But how would I define bond order? So bond order is just the stability of a covalent bond. And that stability is going to be associated with, in a quantitative way, with a number. So how I find it is, it's half the difference between the number of bonding electrons and the number of anti-bonding electrons. So in this case, I have 1/2 times, I have 2 in the bonding MO, or molecular orbital, and I have 0 in the anti-bonding. So I would do 1/2 of 2 minus 0, so ultimately 1/2 of 2, which is going to be 1. Now, this bond order, a bond order of 1, would represent that there is a single bond. A bond order of 2 represents that there's a double bond. And then a bond order of 3, of course, is going to represent that there's a triple bond. We do have half orders that can exist. And usually we think about that if there's going to be an odd number of electrons. So if there's a bond order of 1, it's going to be representing that there's a single bond. A bond order of 2 is representing a double bond. Bond order of 3, triple bond. And then the half orders can happen. And that's, again, if we have that odd number of electrons. Okay, so I can see here that in the H2 molecule, those hydrogens should be attached by a single bond, and we also know that in our previous knowledge that that is true. So in this Mo theory, or in this molecular orbital diagram, we have our bonding, and then we have our anti-bonding Mo's, okay? Bonding are more stable than the anti-bonding Mo's. So this was the hydrogen molecule. Let's look at example, a helium. If we had a helium molecule, so this is H2, or I'm sorry, He2. So in this case, I have a helium atom here, and then I'm going to have another 1s orbital. So I have atomic orbital helium here, another atomic orbital for helium here. Those two orbitals are going to come together, and I want to know what happens when I think about the molecule as a whole. So we're going to separate out. Here's my bonding sigma Mo. Here's my anti-bonding sigma Mo. So I have 2 electrons that are, each of these electrons are going to fill up my Mo's. So 2 are going to fill up here, and then I have 2 more that are going to fill up this. So ultimately, both of the Mo's are going to be full. So it says, if I did the bond order, I would have 2 electrons in the bonding minus 2 electrons in the anti-bonding. So because of that, my 2 in the bonding minus 2 in the anti-bonding is going to give me 0. So that bond order is 0. That's telling me that a diatomic helium does not exist. We know that that's true in nature as well. So this was just a hypothetical, of course, because we already knew that diatomic helium doesn't exist, but we can tell that it's an unstable molecule because I have these electrons that are in this anti-bonding molecular orbital. So this theory can predict diatomic molecules. It predicts that hydrogen exists, and then it as a diatomic, and it predicts that helium doesn't exist as a diatomic. So it corresponds with what we know in nature. Okay, what I'd like you to do, or like you to try, and I want you to hear me well on this. I don't care if you are right or if you were wrong. If you were right, then you are awesome. But if you get this wrong, that is totally okay. I just want you to try, how would I draw a molecular orbital diagram for a hydrogen with a 2- ion? I'm sorry, just kidding. Let's do hydrogen, diatomic hydrogen, with a -1 charge. So hydrogen molecule with a -1 charge. Okay, so that 2 should be in a subscript, but the minus charge should be in the superscript. So H2 with a -1 charge. Show what the molecular orbital diagram would look like for that, and also what would the bond order look like for that. I want you to do the same thing For helium that's diatomic, so He subscript 2, but then an overall positive charge. Okay, so what would that ion look like? So show the Mo diagram, and then also what would the bond order be for that? It is okay if you don't get them right. We are going to practice this tomorrow, okay? This is one of the hardest things to do, I think, in AP Chemistry and chemistry in general. So the fact that you are even willing to try for me is awesome. Okay, so in Mo theory, just some rules that summarize, I think, these principles in the formation of molecular orbitals. So the number of molecular orbitals is equal to the number of atomic orbitals, okay? So if we go back to this, I have 2 helium atomic orbitals. That should be equivalent to the 2 Mo's that I can fill in for helium. That's the bonding, that's the anti-bonding, okay? The second one says atomic orbitals combine most effectively with other atomic orbitals of similar energy. So usually I have to think about what's happening in the 1s, what happens in the 2s, and then we're going to separate 2p because we're going to get to that tomorrow together. So atomic orbitals we think about just on more of an even keel at a degenerate level. Then it says the effectiveness of atomic orbitals when they combine is proportional to their overlap. So ultimately, if I have a larger remember that balance that we said in the video yesterday. There's a balance of how much distance needs to be between the 2 nuclei, so that way I can separate I can minimize my electron repulsion and that nuclear repulsion between the 2 nuclei. So there's a certain way that the atomic orbital should overlap to make a molecular orbital. So each molecular orbital can accommodate at most 2 electrons, just like when we think about our electron configurations or if we're drawing an orbital diagram. And when molecular orbitals of the same energy are populated, 1 electron enters each orbital before spin pairing can occur. So I have to fill in that Aufbau principle, okay? And this is we're gonna see this way more whenever we get into something that has a 2p or something that has a 2s won't do anything. But tomorrow when we do things with 2p, this is where we're going to see this last one. We probably don't see that one so much yet, okay? So these are just some general rules. If we looked at lithium, so we just told you atomic orbitals combine most effectively with others of similar energy. So for example, if we did lithium has a 1s2 that's full, and then it also has the 2s1. So I have 1s2 and then 2s1. I'm going to separate them out. I think about the energy that's just based on the Mo for the 1s orbital. I see that here. And then I'm going to think about what's happening for the 2s. So I have my 2s separated from my 1s. And that's how we'll do Mo's, just because it's easier to think about them on that same energy level, okay? Or thinking about the 2s when they're on that energy level. Thinking about the 1s electrons when they're on that energy level, okay? So tomorrow, we're going to go over those 2 problems that I want you to try, and then we're going to get into what happens. I'll give you a little sneak peek here because it's exciting. What happens when we get into the p orbitals? Look how phenomenal that looks right there. Okay, so we'll talk about those tomorrow. We're also going to do tons of practice with this. Lots more practice with hybridization, as well as polarity, as well as VSEPR, electron domain geometry, all that good stuff. And then I'm also going to get together some multiple choice questions so that way we can practice. And we'll do probably more of the multiple choice stuff on Friday. We'll do more whiteboard stuff tomorrow. Have a wonderful night, and I will see you tomorrow. Also, be ready for a quiz tomorrow. Bye.